Okay, today we're going to talk a little bit about compound events. So like what we did yesterday and what you just did on your quiz is simple probabilities, simple events, because it's one single thing that's happening. Compound events is where you do more than one thing within the experiment, and so it's going to be several different actions happening within one experiment. Now, within compound events, there's two different ways for it to happen. There's what we call independent events and dependent events. So let's talk about the difference in these. So in independent, this is with replacement. This is with replacement. This is where you're going to put it back. You're going to put the card back. You're going to put the marble back. You're going to, whatever, you're going to put it back. You'll see as we go through here. Okay? The second thing is that independent does not effect. What is this? Effect or affect? Does not affect the latter results. Is it effect or affect? Affect is the verb. I don't know. Whatever. Okay, sorry. Okay, and then the last thing is that the total stays the same. Now, for dependent, it's basically the exact opposite of that. So in dependent, it is without replacement. Okay, it does affect later results, and the total is changing. Okay, so we have four different things that are happening here, four different events. And so we're going to decide whether it's independent or dependent. So number one says earning grades on your test and earning your final semester grades. So there's two things happening here that we're talking about. The grade on your test and your final semester grade. Does one of those depend on the other one?
Yes.
Definitely. Your final semester grade definitely depends on your test. So this is a situation that is dependent. One of them definitely affects the other one. Okay, now number two, you select a red apple and then a green apple from a bag of 6 red and 4 green apples. If the first apple is returned to the bag before the next one is selected. So you have 6 red, 4 green. You pick one apple out, see what color it is, then you put it back in. Is the second time you reach in, is it going to be affected by the first one? No, because you put it back in, you put it back exactly like it was. Basically, this is what this is saying, is this is with replacements. You're replacing it. You're putting it back in. So this is definitely an example of independent. Golly. Okay, number 3, selecting a red apple and then a green apple from a bag of 6 red and 4 green if no apples are returned to the bag. So you select one apple out, you don't put it back in. The second time, is it going to depend on what happened the first time?
Yeah.
Definitely, this is an example of dependent. Okay, number 4, tossing a coin and then tossing a die. Does what happened to the die depend on what happened to the coin? Do they affect each other? Nope, they're not going to affect each other. Those are independent events. The coin's not going to affect the die. So this is an example of independent events. Okay, now, let's talk about this. In compound events, okay, what you're going to do with compound events is you are going to multiply the probability in general. You're going to multiply the probability of each event within the experiment. Okay, so if you do 3 different things within this one experiment, you're going to multiply the probability of all 3 of those happening together. So, let's flip it over here and let's think about this example right here. Okay, suppose you're playing a card game with a standard deck of cards and you're dealt 4 cards one after another from the top of the deck. Find the following probabilities. Leave your answers as fractions. Okay, so what's happening is you have a full deck of cards. You're dealt 4 cards. And obviously that implies once you get 1 card, you're not giving that card back. You're given a card, you keep that card. Okay? So within this, what it's talking about here, is this an example of independent or dependent?
Dependent.
This is definitely dependent stuff going on here. Because once you're given that 1 card, you keep it. You do not replace it. So these are dependent events. So what's the probability of there being a standard deck of cards and you are given 4 aces? Just straight off, just 4 aces. What's the probability of that happening? First of all, do you think there's very good probability of that happening?
Depends on if you shuffle it or not.
It's very, very low odds that you would get 4 aces. Very, very low odds. I mean, that's, and so you'll see as we do this. Okay, how many aces are in a deck of cards, in a standard deck of cards?
4.
There's 4. There's 1 ace of each suit. Diamonds, hearts, spades, and clubs. Okay? So there's 4 out of how many?
52.
Out of 52. Okay. So that's the probability of the first part of this experiment, of this event, is the 1 ace. Now we've got to think about this. You were dealt a card, and so now you have 1 of those cards. So how many total cards are you going to have in the second chance here? You start off with 52. There's 52 cards in the deck. You're already dealt 1, so how many cards are left in that deck?
51.
There's 51 cards now. Now, if you choose an ace out the first time, how many aces are going to be left for the second one? There's going to be 3. Okay? Now, the third time you're given the card, how many total cards are there to pick from? 50, because you've been given 2 of them now. And if you choose an ace in the second time, how many aces are left for this one? 2. And then one more time, how many total would be in that fourth one? Now there's 49 cards left, and how many aces would be left if you chose another one that third time? There's going to be 1 ace left out of that now. Okay. So what we're going to do now, as I said, is we're going to multiply all of those events together. All right, so I'm going to go, whoops, nope. I'm going to go, okay, 4 out of 52 for the first time. Then there's 3 out of 51 second time. Then there's 2 out of 50 the third time, times 1 out of 49 the third time. So that's the probability that you would be dealt 4 aces straight off like that. So what this means is out of 270,725 times that you tried that would happen 1 single time, theoretically. You would have to do it 270,725 times before it would happen once. Okay? So would you say that's good odds or low odds?
Low odds.
Pretty low odds. Very low odds of that happening. Okay. So the probability of this happening is 1 out of 27,000 or 270,725 tries. Pretty low odds. Okay. Next time. Now on this one, we're going back to a full deck of cards. So now what's the probability of getting 4 hearts?
13.
Okay, well let's just stop and think about this for a second. Are you going to have better chance of getting 4 aces or getting 4 hearts?
4 hearts.
Definitely, you're going to have way better chance of getting 4 hearts than to get 4 aces. Okay, so how many hearts are in a standard deck of cards?
13.
There's 13. There's 13 of each suit. If you do 13 plus 13 plus 13 plus 13, that gets you to a total of 52. Okay, so what's the probability on with the first card being dealt, what's the probability of getting a heart? 13 out of 52. Okay, now again, you're keeping the card. And so if you get a heart that first time, what's the probability of getting a heart the second time? 12 out of 51. Okay, if you get a heart the second time, what's the probability of getting a heart the third time? 11 out of 50, because there's one less heart, and then there's one less total. And then what's the probability of getting a heart the fourth time? 10 out of 49. And so what we're going to do now is just multiply all of those fractions together.
Just those 4.
Yep. What do you get when you multiply those 4 together?
I got 11 over 4,155.
So what does that 11 out of 4,165 mean? Like in words like I was talking about a second ago.
If you tried it 4,165 times, it would happen 11 times.
Exactly. If you tried to do that 4,165 times, every 4,165 times you tried it, you would get 4 hearts 11 times, theoretically. Okay? And if you did it enough times, if you did this experiment 1,000 times, it would get very close to being close to that. And if you did it 1,000,000 times, it would get even closer. Okay? So, are there better odds of getting 4 hearts than there is of getting 4 aces? Way, way, way better odds. Way better odds of getting this than this. All right, now, what's the probability of getting 4 face cards? Now let's think about this. How many face cards are in a standard deck of cards?
12.
Okay, good. Because how many face cards are there per suit?
3.
3. There's a king, queen, and jack. Like there's a king, queen, and jack of hearts. There's a king, queen, and jack of diamonds. There's a king, queen, and jack of spades. And a king, queen, and jack of clubs. So 3, 3, 3, 3. There's 12 face cards. So what's the probability of getting a face card in the first card you get? 12 out of 52. There's a total of 52 cards, and there's 12 face cards. Now again, we're keeping it each time here. So what's the probability of getting a face card the second time? 11 out of 51. What's the probability of getting a face card the third time? 10 out of 50. And then what's the probability of getting a face card the fourth time? 9 out of 49. So what's the probability of choosing 4 face cards?
99
over 54,145.
Okay. Now, is there better chances of getting 4 face cards than there is to get 4 aces?
Yes.
Yes, way better odds. Is it better odds to get 4 face cards or 4 hearts?
Or hearts.
Okay. So, yeah, it's easier to get that. What if this was closer than this? Because this, I mean, it's pretty obvious, but how could you tell, what would be the best way to tell the difference if these were kind of close to each other?
The smaller.
Well, the bottom number is different also, so what would be an easy way to compare these two things?
Divide.
In the decimal.
Get it as a decimal. What is 11 over 4165 as a decimal?
0.02641.
0, 0, 0,
It's 202641.
2641 like that.
Can't you do percent as well?
Yep. Which, we'll do that in a second, but the 99 over 54, 145, what's that as a decimal?
0.001828.
Like that?
Yeah.
Okay. So, of getting 4 hearts, what's the percentage of that happening?
0.26%.
0.26% of that happening. That's less than 1%. That's a quarter of 1%, so that's very low odds. This one is 0.18%. So it's less. This one up here is a very, very small number. Okay, now this last one. Probability of getting an ace, a king, queen, and jack. So what's the probability of getting an ace in the first card? 4 out of 52. Now, what's the probability of getting a king on the second one?
4 out of 51.
4 out of 51, because if you choose an ace out, does that affect getting a king the second time? No, it still is 4 kings left. But we do still have that one card, so that does drop that number down, because now there's only 51 cards. So what's the probability of choosing a queen the third time? 4 out of 50, and then probability of choosing a jack the fourth time is 4 out of 49. And what does that give you?
32 over 8. 12,175.
Okay. So that's the idea on that. Those are dependent events, okay? These down here are easier because on this one, you're going to spin 2 different spinners. This is an example of independent events right here, okay? Because what you spin on the first spinner doesn't affect the second spinner. Obviously, they're independent of each other. So on number 9 there, we're only going to do 9 and 10, so I'm not going to do 11 or 12 here, but on 9, what's the probability of spinning an A and a 2? So what's the probability of spinning an A on the first one? Is 1/5.
And 2. Oh, 1/3.
And then what's the probability of spinning a 2?
1/3.
Okay, there's 2 2s. So that's 2 out of 6, or 1/3. So when you multiply those, you get 2 over 30, which is 1/15. So again, what does 1/15 mean? Okay, good. Out of every 15 tries, you would get the A and 2 one time. Okay, number 10. What's the probability of spinning and getting a vowel on the first one and getting an even number on the second one?
1/5.
Okay, so what's the probability of spinning a vowel? 2/5. A and E are 2 vowels. So 2/5. And what's the probability of getting an even? There's 3 evens, so 3 out of 6 or 1/2. So that's going to give you 6 over 30, which would simplify down to 1/5. So that means out of every 5 tries, that would happen once. So that's pretty good odds of that happening.